So now we're moving on to when you have to do substitution with definite integrals. Again, definite integrals are when you have an upper and lower limit of integration. So you just need to remember these are the ones where you want to be sure to either, you have options here, to either change the limits of integration or resubstitute at the end. You've got to do one or the other though, because otherwise you'll end up with the wrong answer. And side note, I think it's easier to change the limits. Oh my gosh. Okay, easier, not either. Easier to change limits. Okay. So for number 8, and this is, I just took this verbiage from the book so that you could get familiar with what the book says so you can understand it. It wants you to make a U substitution, which basically means do what we've been doing and integrate from UA to UB. I'm going to show you what that is in a second. That's when you change the limits of integration. So again, this is tricky because it's like, whoa, which one do I call U? What's going on? I don't know what to do. Okay. And then with cosine and sine especially, either one could be the function of the derivative because one's the derivative of the other and vice versa. But notice right here that cosine is inside the negative third power. And we don't know an antiderivative for that. So that's the one we're going to want to call U. Because we can do an antiderivative of U to the negative third. But we can't do one of cosine to the negative third. So I'm going to let U be cosine of 2 theta. And then that will make du is going to be, if I use chain rule, because I need chain rule here. So du is going to be 2 sine 2 theta. Oh, sorry, negative, excuse me. Negative 2 sine 2 theta and then d theta. So then d theta becomes du divided by negative 2 sine 2 theta. Okay, so that's step 1. Now notice back at the beginning of this lesson, I said for step 2, when you're doing the definite integrals, to change the upper and lower limit. So that's what I'm going to do right now. So right now the lower limit is 0 and the upper limit is pi over 6, but that's when I'm talking about theta. But if I want to change it to u, so like if I want to do u of 0 and u of pi over 6, u is cosine of 2 theta. So u of 0 would be cosine of 2 times 0. And cosine of 0 is 1. So this would be 1. And then u of pi over 6 is cosine of 2 times pi over 6. And cosine of, which would basically be pi over 3. I'll write that down. So that's basically pi over 3. And cosine of pi over 3 is 1/2. Okay, so we changed the limits of integration. Okay, then for step 3, I am to now substitute. So I'm going to substitute both the function and the limits of integration. So this integral is not going from 0 to pi over 6 anymore. It did that when it was theta. Now it's going to go from 1 to 1/2 and keep the order here the same as it was here, even though now the smaller number is on top. It's okay. Okay, so this is what it means. This is u of a, this is u of b. So that's what it means right here. Okay, so now I'm going to substitute in the values for cosine and sine. So this becomes u to the negative third. So not cosine 2 theta to the negative third, u to the negative third. And then the sine 2 theta is still there, but it's about to get canceled out. And then the d theta becomes du divided by negative 2 sine 2 theta. So those are going to cancel out, and I'm going to be left with the integral from 1 to 1/2 of u to the negative third du, and then divided by negative 2. I guess I'll just leave it there. For step 4, I'm going to go ahead and integrate. I'm going to pull the negative 1/2 out. And I'm going to have the integral from 1 to a half of u to the negative third du, which ends up being negative 1/2 times u to the negative 2 over negative 2, because you add 1 and then divide. And then I'm going to evaluate that from 1 to a half, because this is not a plus c problem anymore. This is a definite integral. But let me first just multiply all this together, and then I will evaluate. You can either evaluate and then multiply by negative 1/2, or multiply by negative 1/2 and evaluate. I think for me, it's easier to multiply first and then evaluate. It's up to you how you want to do it. So this would become positive u to the negative 2 divided by 4. And then evaluate that from 1 to a half. And actually, sorry, I should have done one more thing. That's the same thing as 1 over 4u squared from 1 to a half. So this is 1 over 4 times a half squared minus 1 over 4 times 1 squared. So, oh gosh, what's that? That's going to be, well, 1/2 squared is 1/4. So then that's actually going to end up canceling. Here, I'll just go down here. So this is going to be 1 over 1, and then minus 1 over 4. And so it ends up being 3/4. Okay, that wasn't that bad. It looks scarier than it was. So that's the answer for number 8, is 3/4. And that's how it works when you have to do a definite integral. And I really strongly advise this method. Don't resubstitute at the end. Just change the limits, and it's so much easier. Oh my gosh, you'll find it's so much easier. Okay, separable differential equation. This is like part 2 of 6-1, where basically you separate the variables and integrate both sides. Oh, and solve for y. Just kidding. Integrate both sides. Don't stop there. And solve for y. So this was the major thing that we learned in 6-1 part 2 and part 3 actually. But it's a crazy, scary looking equation. And heads up, you're going to have one crazy, scary looking equation very similar to this one on chapter 6 test. Okay. All right, so we need to separate the variables, meaning y's have to go with dy's and x's have to go with dx's. Oh, yeah, and it's telling us to solve the differentiable equation. That means this is dy dx. That means find y. Okay, so I'm going to divide both sides by square root of y and cosine squared of the square root of y. And I'm going to multiply both sides by the dx. So this is step 1 of that process. Then, as you recall, we would integrate both sides. And this right side is looking easy peasy. So I'm going to do that one first because it doesn't scare me as much as crazy monster over here does. Okay, let's tackle this monster here. So I'm going to need to use a u substitution. So keep in mind, when you're doing differentiable equations, you could end up having to also do a u substitution as well. You know, like I said, they could pop up anytime, any place, and you have to be ready to deal with them. So I'm going to decide what to call u. I need to decide what to call u. And this one's kind of easy because I see the rad y. I want to get rid of the rad y because this is another one of those problems. Let's rewrite this. This is one of those problems where it's like you have 1 over rad y times really secant squared rad y. That's really what we have. And then all of that times dy. Because it's 1 over cosine squared. That's really secant squared. And then it takes the fraction part of it out. It also reminds us, oh, that I really want to take the antiderivative of that because that's just tangent. So let's just get rid of the rad y, basically. So I'm going to let u be rad y, which basically means u is equal to the y to the 1/2. So then du would be 1/2 y to the negative 1/2 dy. So then du is 1 over 2 rad y dy. So if I multiply that, then 2 rad y du is equal to dy. So if I go to substitute that back in, I get the integral of 1 over rad y times secant squared u times 2 rad y du. Okay, those rad y's, as predicted, are going to cancel out. And I have the integral of secant squared u, 2, because there was a 2 there, 2 secant squared u du. Okay, meanwhile, back at the ranch, we still had x squared over 2 plus a constant. Whew, almost done. Almost done. Okay, so let's take the 2 out of here. And I got this equals that. And I'm going to move this over here. So the antiderivative of secant squared is tangent. So that this basically becomes 2 tan u, of course, plus a constant. But we're going to let this one here be combined constant. So that's a combined constant there. Okay. Then in this case, I need to substitute back because I need to solve for y. So I need y to go back in there. So u was the square root of y. So I'm going to go ahead and put that back in. So we get 2 times tangent of the square root of y is equal to x squared over 2 plus a constant. But I need to solve for y. My first step is to multiply both sides by 1/2 to get rid of the 2. So then this will become a 4. And then this will just be some other constant, but I'll just keep calling it c. Okay, now I need to get rid of the tangent. So the way we do that is we take the inverse tan of both sides. Because inverse tan and tan, they undo each other or they cancel each other out. So that gets rid of the tan right there. So then the square root of y is equal to the inverse tan of that blob, the x squared over 4 plus whatever that constant is. And then last but not least, because I want to get y all the way alone, I need to square both sides, which is also another use of an inverse because the squaring function and the radical function are inverses of each other. They also undo each other. Okay, so then this becomes y is equal to the inverse tan of x squared over 4 plus a constant, and then that whole function squared. Now, some of you, unfortunately, might be wondering why we did not multiply the 2 to this power. This is not a power. And I know that's confusing. I feel your pain. That's not a power. That's just a notation telling me that this is the inverse tangent as opposed to regular tangent. So no, do not think that these are powers. We don't use any power rules here. We just say, okay, this is the inverse tan of this, and whatever that value is, I'm going to square it. And we've actually finally solved this crazy hard problem. Okay? And so I put a star by it because, yes, there will be one this crazy hard on your test. There could be one this crazy hard on the AP test. So you got to be prepared. All right, so if you have any questions, please come find me in tutorial. Also, I'll be in the libraries every Monday from 3 to 5. And also, I'm opening up an additional hour of my time after school on Tuesdays. I'm going to start making myself available on Tuesdays from 3 to 4. So feel free to come find me, get some help from me, whatever you need, and I will see you in class.